calculus students. In today's lesson, we're going to look at an application of integration, which is going to take us into three-dimensional space. And we're going to do so by learning how to calculate volumes of solids of revolution. Learning objective for this lesson is to calculate volumes of solids of revolution using definite integrals. Although the first thing we're going to do is we're going to come up with an integral expression that we can use to determine the volume of a solid, and then we'll worry about how we can do it based on the volume of solids of revolution. So I'll start off with a three-dimensional shape. This is just an ellipse in 3 dimensions, so just an ellipse that has depth to it. If you look at the different the coordinate axes, the blue axis, which points like vertically upward and downward towards the top and the bottom of the page, we could call that the y-axis. The red axis that points towards the left and the right side of the page, we can call that the x-axis. And the green one, that would be the z-axis. So from our perspective, technically, that'd be coming into and out of the page. Now, I'm going to call this shape that we see here an arbitrary three-dimensional solid. And the idea is we want to calculate the volume of the solid between two regions, specifically between two planes, x equals a and x equals b. Now, if this were an area calculation, we would just draw a line that passes through the x-axis through x equals a, and a line that passes through the x-axis at x equals b. But since we're now dealing with three-dimensional shape, we can't just draw a straight line going through those two different parts in the x-axis. We have to draw planes. So in terms of what the planes would actually look like, you would have a plane that passes through the x-axis, x is equal to a, another plane that passes through the x-axis, x is equal to b. And based on the way that I've just identified the coordinate axis, both x equals a and x equals b would be parallel to both the y-axis and to the z-axis. Or we could say that both those are parallel to the YZ plane. So our goal here is just to find some kind of mechanism to calculate what the volume of the solid is in the region between those two different planes. The way we're going to do that is similar to how we figured out the area of a curve between two different points. So when we figured out the area of a curve between 2 points, what we did is we took the curve and we looked at the region from the curve to the x-axis, and we broke it into an infinite number of rectangles. Now, we can't do rectangles here because, again, the shape we're looking at actually has depth to it. So instead of breaking into rectangles, we're going to break it into a really thin shape that has depth. So think of it as like you have a loaf of bread, and then between those two different regions, from x equals a to x equals b, you're going to make like really, really thin slices. So it's almost like the shape is a loaf of bread, and we're going to cut the section between x equals a and x equals b into like really, really thin chunks or slabs, albeit the word we're going to use right here is a disk. And we're going to look at just one disk, what one disk would look like. So if we go back to my picture, just showing the volume we want to calculate from x equals a to x equals b, we'll show one of those disks. Now, again, the disk I'm showing right here, it looks like it's pretty thick, but technically speaking, this disk right here would have a thickness that is infinitely small. Because again, the more of these disks you can put in between the region from x equals a to x equals b, the better representation you're going to have for the volume. So we'll label this. So the thickness of the disk, we're going to call that delta x. Although when we turn this into an integration statement, we're going to write it as dx instead, because again, dx just means it is like an infinitely small thickness to it. And then we'll say A of xi star is the cross-sectional area of a plane that intersects the solid perpendicular to the x-axis. So the cross-sectional area on this shape right here, I'll just highlight it with red. It would be this little section right here. And it appears as though it has like a shape. It's hard to see like what the shape is just because of the perspective we're looking at, but it's something along a circular cross-sectional shape. And A of xi star just means the cross-sectional area at at some kind of generic position. Generic position just being x I star, so somewhere along the x-axis between x is equal to a and x is equal to b. So again, we label that a of xi star. And then if I want to calculate what the volume of one of these disks are, you can think of this similar in terms of how you would calculate the volume of a cylinder. So most times our cylinders are oriented a little bit differently. Like you'd have the cross-sectional area that you could put flat on a horizontal surface. Here it's just a bit different. The cross-sectional area is more aligned vertically. And if you want to calculate the area of a cylinder, you would just take the height of the cylinder. So in this case right here, that's delta x. Then you just multiply by the cross-sectional area. So that's how we're going to calculate the volume of one of these disks. So VI would just be the volume of like the ith disk, or just one of the disks in between x equals a and x equals b. It doesn't matter where it is as long as it is between those two different points. And that would just be equal to a of xi star. So that's the cross-sectional area of that disk multiplied by its thickness, which is delta x. Now, that doesn't give me the volume, though, that of the entire shape between x equals a and x equals b. That only tells me what the volume of a single really thin disk is. So if we want to figure out what the total volume is, well, we have to take all of those ridiculously small disks with like really small thickness, and we need to add them all together. And if we add them all disks together between x equals a and x equals b, then we'll have what the total volume is. Now, we're going to define this in a couple of different ways, because you would technically need an infinite number of disks to get a good representation of what the volume is, but you can't have an infinite number of disks, so it's not a finite number. We're going to represent that as a limit. So what we would say is the volume is equal to the limit as n approaches infinity. N would just be the number of disks that you're fitting in between the region from x equals a to x equals b. And then we have the sum from I equals 1. So I equals 1 would just be where the first disk going all the way to n. And again, we're doing a limit because again, the idea is to get the more disks we can get, the better representation of the volume. And then we would have within the sigma notation, we have a of xi star multiplied by delta x. So if you did expand that, like the first disk would have a volume of a x1 star delta x. The second one would have a volume of a x2 star delta x, and then so on. And you just keep doing it, adding those different volumes together until you have like the best representation of what the volume is. Now, we're going to write this as an integral, though, because obviously it's much easier to evaluate integrals compared to limits. So what we can say is, we can say the volume is equal to the integral in going from a to b of a of x dx. Now, the way to physically interpret what this means is, what this integral tells you is you would take this three-dimensional shape. The dx is saying you just you make a bunch of different cuts where the thickness of each one of these disks is dx. Now, it would be delta x, but again, if it's an infinitely small thickness, we just change the delta to a d. So if we take one of those disks and we take its thickness and we multiply what its corresponding cross-sectional area is, well, that would be the volume of a single disk. But then the integral is telling you we're going to add all disks together from x is equal to a and to x is equal to b, and then we can get a good, I don't want to call it good estimation, but we'll actually get what the volume of that three-dimensional shape is going to be. Okay, now, we're then going to extend this to calculating something referred to as volumes of solids of revolution, because that's the main learning objective for this lesson. So let's look at a three-dimensional picture. So we have a function, y is equal to f of x. Now, I'm going to change the perspective of the coordinate grid a little bit. So now, when I look at the coordinate grid, we're going to make the red axis here. This is going to be the x-axis. And then the green one, that's going to be the y-axis. And the z-axis is going to be this blue one. Now, the function I'm currently looking at is just a function in 2 dimensions. It just says y is a function of x. So this black curve right here, that's y equals f as a function of x. That function just starts off in two-dimensional in 2 dimensions, okay, in that 2-dimensional plane, the y-x plane. So if you were to view this picture from a top view perspective, like you would just see the y-axis going towards the top of the page and the x-axis towards the right of the page, and you'd have the function within that. But we've just rotated the coordinate grid, so because we're about to do something to turn this function and form a 3-dimensional shape out of it. So let's say that A is going to be a line that passes through the x-axis at x is equal to 1 in this picture. And then we'll say that B is a line that passes through the x-axis at x is equal to 4 in this picture. And then what we're going to do is we're going to shade in the region that's bound between x equals A, x equals B, the function, and the x-axis itself. So that's that purple shaded area. We'll call that capital R. So again, capital R would just be the region that is bound between x equals A, x equals B, the function y equals f of x, and the x-axis. And that function is a quadratic function. And I'll show you in a moment here because I'm going to use a little bit of an app to show how we can get a volume by taking an area bound there and rotating it. So now we're going to do, like I said, I'm going to show this like almost essentially right away, is we're going to take this bound region and we're going to rotate it about a particular axis by 1 revolution. So 1 revolution just being 360 degrees. Now, if we take that 2-dimensional shape and we rotate it 360 degrees, and the axis we're going to rotate it about in this particular situation is the x-axis, we can actually form a solid shape that has depth to it. So we'll have a shape that we can calculate the volume from. Okay, now I'm going to show you how I do this. So again, like my preferred program to use on the internet for constructing graphs or just anything graph related is a program called GeoGebra. So I'm going to go to the app right here and just show you how I can actually form this 3-dimensional shape by taking this region and doing a revolution about the x-axis. So we'll just discard this here for a moment. Okay, and then we're going to go over to this. All right, so I'll make this screen a little bit bigger right here. Okay, so again, blue, the z-axis, x is the red one's the x-axis, and then green is the y-axis, and I can see my shape here. So the shape, by the way, does have an equation that would be y is equal to 0.1 x squared. So just your base parabola that has a vertical stretch factor of 1 over 10. Now, I've set it. So what we're going to do is I'm going to start at x is equal to 1. We're going to go to x is equal to 4. And then this little slider right here is going to allow me to take this shape between x equals A, x equals 1, and x equals 4, and rotate it about the x-axis. Now, watch what happens when I do this. So I start to take this, and I begin to take that shape bound between the function and the x-axis and rotate it. So now I've gone through about 90 degrees here. I keep going, okay? And now I've gone through half a revolution, okay? So we're at 180 degrees here. And then I just keep going. And then now I've rotated this 2-dimensional shape now about the x-axis by 270. And we want to do 1 full revolution. So we do 1 full revolution, then we get a shape that looks now like this. So what we did is we started with a shape in 2 dimensions, and we took that shape and rotated it about a particular axis. And now I have a 3-dimensional shape to it. It looks kind of like a funnel or like a cone type shape. And what we want now is we want to find a way to calculate like what is the entire volume within this entire region of the shape right here. So we'll go back now to the PowerPoint and kind of identify how to do that. But that's the idea is, again, you start with your shape in 2 dimensions, and by rotating it about a particular axis, you can actually form a shape in 3 dimensions. All right, so let's go back here now. So again, this is what the shape looks like, albeit maybe the perspective is just a little bit different compared to what I showed on the previous slide. And now this would be a small little disc that would be, because again, the idea is if we want to calculate the volume of like this shape right here, then we need to break it into an infinite number of small little discs. And then by adding all those individual discs together, we can get what the volume of this shape would be. So once again, A of x, that just represents the cross-sectional area of what the disk would look like. So that's this here. Now, it doesn't look like it right here just because of the perspective that we're examining, but this cross-sectional area is circular. It looks like it's more of like an ellipse or oval type shape to it. But again, if we were to view this directly along the x-axis, we would see that that cross-sectional area is circular. That's important because that's going to be, we're going to need to use that fact when we start to calculate the volume of the shape in just a moment here. And again, one of these discs, so again, one of these thin slices of this like three-dimensional cone type shape. Again, the more of these discs you can fit in, then the better representation of the volume you have. So the best representation is we want to have an infinite number of discs there. And if we have an infinite number of discs, they have to have a ridiculously small thickness. And that's what we use the dx element to show that we have an infinitely small thickness to it. So again, we go back to, so what exactly, how would we calculate the volume? And again, make sure you understand like what this integral is actually telling you. Like, yes, we will get a function for A of x. We will integrate it with respect to x with these limits of integration. But again, what this is telling you is it's saying, look at the shape from A to B. What we would do is we take that shape and we break it into an infinite number of tiny little discs with a thickness of dx. To calculate the volume of one of those discs, we take that thickness and we multiply by its cross-sectional area, but that only gives you the volume of a single disc. So the integration portion is telling you from A to B, we're going to add all of those discs together. And then by adding all those discs that have an infinitely small thickness together, then we have a representation of what the volume of that 3D shape is. So the main complication in doing problems where we need to do this is we have to figure out what an equation for the cross-sectional area is. Because once we have an equation for the cross-sectional area and we know the limits of integration, we just have to find the antiderivative of what A of x is. So this depends on two things. One, it depends on what your function is, obviously, because if you have different functions, they're gonna form different shapes when you rotate it about a particular axis. And then two, it also depends on what axis you rotate it about. So in this problem, we chose to rotate it about the x-axis, but we could also rotate this two-dimensional shape, this region bound here, about a different axis. Like we could rotate it about x is equal to 2, or x is equal to -1, or we could rotate it about the y-axis. And you'll see how this works out when we do a few of the examples in just a moment here. And by a moment here, I mean like right now. Okay, so we started off by identifying the way that we're going to calculate volume is we break this into, we break this shape into an infinite number of discs. So this problem here says, consider the region bound between the equations y is equal to 1 over x. Okay, let's label this. So this right here, this is my function. Y is equal to f of x. Okay, we want to look at the region bound between the function. X is equal to 1. So I'm going to go over here and I'm just going to draw that line going through. X is equal to 1. So that's right here. Okay, and that's going to be my lower limit of integration. Then we'll do, we're going to x is equal to 2. So that's going to be located here. So x is equal to 2. And then what we're going to do is we want to look at the region that's bound between the function, x equals 1, x equals 2, and we're going to do a rotation about the x-axis. So it says also bound about a yeah, the region is bounded about y is equal to 0. And then after we form that region, so I'll kind of just show it with purple right here. Okay, so that's the region that's bound. So again, the way to think about it is we're going to take this two-dimensional shape and we're going to rotate it with respect to about the x-axis. Now, part C of the problem says sketch what this solid would actually look like. Now, I think I'll actually do that first just to show you like a rough idea of like what the solid is going to be and just like where do we actually get the disk. So let's start off with, I'm going to erase the purple here actually, just because otherwise it's going to be like two colors that are overlapping. So I'll just get rid of this. We know which region we're going to rotate here. Okay, and then we'll try to get an idea of like what the three-dimensional shape looks like. So I'll do this in purple. Okay, so the idea is, okay, we're going to take, if you compare the function at x equals 1 to the x-axis, this is going to be kind of like as high as the function is going to go when we rotate it. So if I want to show what a disk would look like if you rotated about the x-axis, we would take this little point right here, and we're going to rotate it. Now, if it goes up to +1 and you rotate about the x-axis, then it has to go down to -1 if you'd rotated about the x-axis as well. Okay, you got that symmetry there. So we'll take that, we'll rotate it. Okay, and that's what the disk would look like at x is equal to 1. Okay, so we've got a circle that has a pretty large radius to it. And then what we're going to do is we're going to do the same thing at x is equal to 2. So we're taking this, we're rotating it here about the x-axis. So if I do that, if I rotate the shape about the x-axis, so this looks like it's about 0.5. So if it's 0.5 on the top and you rotate it, it would then be negative 0.5 on the bottom. So this is as low as this portion is going to go. Okay, rotate it, and then it looks like that. And then what we're going to do is we're just going to make this symmetrical. So this portion of the curve that goes from the top of this one to the bottom of that one, we're also going to make it go just something roughly like this right here. I didn't do a very good job of like sketching that, but it should be perfectly symmetrical. So now, if we actually show what the shape would look like, okay, I'll kind of shade it in for you here. So the shape would look like this. So it's kind of got like a funnel cone type shape to it, except it looks like the bottom portion of the cone has been like cut off. But that's your three-dimensional shape that we're going to get. Now, what we need to do is we need to get an area, an equation for the area of one of these disks. So to do that, we're actually going to look at a disk that's somewhere in between x is equal to 1 and x is equal to 2. So I'll illustrate that with a different color. I'll do it in red here. Okay, so let's just pick an arbitrary point between 1 and 2. Okay, let's track that point up to where the curve is. And then what I'm going to do is I'm going to rotate it about the x-axis, and I'm going to just show the shape of what my little disk looks like. So this is going to be one disk. Okay, so it's going to go down like that. It's going to go up like this. Okay, let's draw the cross-sectional area, kind of like that. And then I'm going to add a little bit of thickness to the disk. And I'm really going to exaggerate it here just because, again, like obviously the thickness needs to be, the thickness should be infinitely thin. So if we label this right here, okay, this little dimension, that would be dx. And then this cross-sectional area, here, I'll use a different color to point it out to you. So let's do green right here. So this cross-sectional area, that has an equation of a of x. So again, we're going to get like just the area of one of these disks, and then the integration statement is going to be able to put everything together. All right, now to do this, okay, we're going to go back to this picture in 3 dimensions. In 2 dimensions. So let's go over here. And again, we'll just show what my limits of integration are. So we're going from x is equal to 1 here. Okay, so we're not going to draw it in 3 dimensions right now because what I need to do is I need to get an equation for what the cross-sectional area is. And then we've got x is equal to 2. So we go up there. X is equal to 2. Now, I'm going to draw my disk that's between 1 and 2 from a side view perspective. So from a side view perspective, it would be a disk that has like a really, really tiny thickness to it. Now, if it has an infinitely small thickness, we can just draw this as being a straight line. Like I'm drawing with a little bit of thickness right here, but technically this would have like an infinitely small thickness. Okay, now remember that when you rotate this, this is actually going to form a cross-sectional area that's a circle. So in order to get an equation for what the area is, I need to know what an equation for the radius is, because the area of a circle is just going to be pi times r times squared. So let's actually even write that out. So we'll say A, what's the area? So the area is equal to pi times r squared. And again, the disk, even though it doesn't look like it right here, the cross-sectional of the area of that disk is a circle. Okay, now, the thing is, though, if you look from x equals 1 to x equals 2, the radius is changing. Like it starts off as being like a disk on this side would have a bigger radius compared to the disk on that side would have a smaller radius. So we're actually going to have to write down the radius as a function of x as well because it is changing. Now, what this dimension represents right here, since we're rotating about the x-axis, this entire dimension right here, that is the radius of what the disk would be. We're going to call that r as a function of x. Now, in terms of what r as a function of x is, well, it's just the value of the function. So again, your function right here is y is equal to f of x. So your radius would just be the value of y of the function at x. So r of x right here would just be equal to whatever the value of the function is at the position of that disk. So we'll just write down r of x is equal to f of x. Okay, so now this equation, we're going to change it a little bit right here. So because the disk, the cross-sectional area depends on like what the position is between 1 and 2. So we're going to say area is a function of x, and that's equal to pi. And again, the radius also depends on like where the position of the disk is. So we're going to also define that as r as a function of x, and we're going to square that. But again, we already looked at the picture right here and identified, well, what is the radius? It's just whatever the y value of the function is. We'll say it's pi. So we'll say pi, and then multiply by f of x all squared. Okay, so then, well, we know what f of x is. F of x is 1 over x. So if I plug this in, we would then have an equation for the area of this disk, cross-sectional area. So we'd have a of x would then be equal to pi multiply by 1 over x all squared. So a of x would be equal to, we'll apply that exponent to both the top and the bottom. And then we would have a of x would be equal to pi times 1 squared, so just pi over x squared. All right, so area is pi over x squared. And again, this makes sense. You have like an inverse square relationship. So as you make your way progressively towards the right, as x gets bigger, the cross-sectional area of all the disks are going to get a little bit smaller. Now, B wants us to actually calculate the volume. Okay, so now let's write down our volume statement as an integral. So as an integral, we know that volume is equal to the integral in going from A to B of the cross-sectional area of a disk times its thickness. But we can now be much more specific because we know what A and B are. We're going from 1 to 2, and we also now have an equation for what the area is. So we would then have volume would be equal to the integral and going from 1 to 2. Okay, we're going to substitute in what my area equation is. That area equation was pi, all divided by x squared. And then we are going to integrate that with respect to x. Now, to integrate this, let's do a couple of things. So pi, that's a constant. So we'll take that out of there, constant multiple. And then we need to move the x squared up to the numerator just so we can actually apply the power rule for figuring out an antiderivative. So then this would be your volume would be equal to, we'd have pi, and then we're going to find the integral from 1 to 2 of x to the negative 2, and we're going to integrate that with respect to x, so dx. Okay, so now it's just a matter of just figuring out an antiderivative. So this would be pi, and then, okay, the antiderivative of x to the negative 2 would be negative x to the negative 1, and then we're going to integrate that. So we're applying the fundamental theorem of calculus part 2, and we're going to integrate that from 1 to 2. Now, always pull out a constant multiple as much as you can. So if you can pull out a constant multiple where you integrate, that's good. You can also pull out a constant multiple before you evaluate what this integral, evaluate the actual antiderivative. So I can then write this as, this would be equal to negative pi. And then we would just need to evaluate. We're going to say 1 over x, and we're going to evaluate that from 1 to 2. So now my volume would be equal to negative pi. And then we evaluate the antiderivative by subbing in the upper limit first. So that would be 1 over 2. And then subtract, sub in the lower limit. So 1 over 1. But we need to have a common denominator here. So let's just multiply the second fraction by 2 over 2. And then we would have my volume would then be equal to negative pi multiplied by, and then this would be 1 minus 2, which would be negative 1 over the common denominator of 2. And then I would just have, well, negative times a negative is a positive, and then we have an expression for what this volume is. This volume would then just be equal to pi over 2. So relatively easy antiderivative to calculate. Okay, now that's only one representation of how you can find the volume. So sometimes based on the function you're given and the axis of rotation, when you rotate, the cross-sectional area is a disk, but that's not always going to happen. Sometimes when you do a rotation, you can actually have a disk with a hole in it. So if you have a disk that has like a little tiny hole in it, like this, that's referred to as a washer. Okay, so we'll see like why do we need to actually use it for this particular example. Okay, so it's getting a bit harder now. So it says, consider the region bound between the equations y is equal to x squared. Okay, y equals x squared. That's this parabola that would be in green here. And then also between y squared is equal to x. So that's a parabola that just opens towards the right. Okay, and it says we're going to rotate this about the x-axis to form a solid. And again, I want to derive an equation for the area of the washer. I want to calculate the volume of the solid form, and I want to sketch the washer and the solid directly on the provided grid. Okay, now the region that is bound here is just between the two different functions. So that's going to be this region here. Now, I would say the issue with this problem is that you don't know what the lower limit of integration is, and you don't know what the other upper limit of integration is. Now, if you look at the picture, you can clearly see you're going from 0 to 1, but oftentimes you're not going to be given a diagram of like what the actual functions look like. You just need to look at the functions and do this. So what we want to do is we actually want to figure out what the intersection points are between these two different functions, because the intersection points will tell me where do you have A and then where do you have B. So this point right here, this is where you would have, so this is the first time they intersect. So this would be where you have x is equal to a. And then the next one right here, this would be x is equal to b. Okay, let's figure those intersection points first, and then we'll go ahead and we will actually try to figure out. I'll show you what the shape looks like if we do rotate it. Okay, so to figure out the intersection points, what we are going to do is we just need to, this isn't really part of part A, but it's going to be useful when we get to part B because we do need to know the limits of integration. So we just need to wait to set these two equations equal to each other so we can actually figure out what the intersection points are. So we'll take this first equation. We'll say it's y is equal to x squared. So that's the first one. Now, this second equation, which is y squared, is equal to x. What I'm going to do is I'm going to take the square root of both sides of it. So we'll square root this side. We'll square root that side. And then what I would have is we would have y is equal to plus or minus the square root of x. Okay, now what I'm then going to do is I'm just going to directly substitute that into this equation over here. So if we do that, I would then have so we'll take this y value. We're going to take this. There's other ways you can solve it too, but I can just do it like that. So we're going to take this and plug it into the equation right there. So what it'd then look like is you'd have plus or minus square root of x would be equal to x squared. Now, if I want to solve for what x is, we got to get rid of that radical. So we'll just square both sides of the equation. And if you do that, we would then be left with, we would have x on the left-hand side, and we would have x to the power of 4 on the right-hand side. Let's move all these terms over to the same side. So then we would have x to the power of 4 minus x is equal to 0, and we'll factor. So we would have x, and then we would have x cubed minus 1. And then we can clearly see from the zero product rule what the two different values of x are. So for the first factor, we would have x is equal to 0. And the second factor, I mean, if you added 1 to the other side and took the cube root, you would get it's equal to 1. So I now know what my starting point is for the intersection between those two curves. And I know what the ending point is actually going to look like as well. Okay, now, this is where it gets a bit weird. So now what I'm going to try to do is I'm going to try to show you what happens if we actually rotate this shape about the x-axis. So I'm going to get rid of the purple here. Again, just to hopefully make it a bit more clear. Now, if we start at x is equal to a, well, x is equal to a is already a point that's directly on the x-axis. So if you take this point on the x-axis and you rotate it 360 degrees, it's still just that same point. So it stays right there. There's nothing to show. Now, over here, what would happen is, so this is my second intersection point. Now, this one, we can actually do a full rotation about the x-axis. Now, you'll also notice, though, it's just a point, though. Like, we don't actually have any, like, area that we're rotating about the x-axis. So if I rotate this one, it's going to look just something like this right here. It's kind of showing, it's going to be like just basically a really big hole. Okay, really big hole, and it's going to have a radius that would just be equal to 1 at the end right there, because you can see it lines up with the y-axis at 1. Now, what you then want to do is we want to shade some of the region in here. Now, here's where it gets a bit more complicated, because what you need to do is this is the region bound between the top function and the bottom one. So the function doesn't go completely down to the x-axis. So what you'd be doing is you would take this area and you would rotate it directly about the x-axis. And then we'll make this symmetrical on the bottom side as well. So I'll just take this little green thing here and just kind of make it go in a direction that goes like that. And then we're going to have similar thing. We'll just shade in this region like this. Okay, now here's the issue. So now what we're going to do is we're going to draw the cross-sectional area of what this thing looks like. But the thing is, because the function doesn't go down to the x-axis, you're going to have a little bit of a hole here. So I'll show you how the hole works. So let's say we want to do a disk at, I'll just pick 0.5 as an arbitrary point. Okay, now above and below, this is where the actual region bound starts. So if we do a full rotation, we're going to get a hole that looks like that. Okay, now if we go up to this point at x equals 0.5 and down to this point at the same thing right here, okay, this is going to actually show me like the outer radius of what this washer is going to look like. So if we draw that, okay, it would look something like this. Okay, shade that in. Let's add some thickness to it. And then what we would have here, so we have a washer with a tiny thickness. We call that dx. And then cross-sectional area, we call that a of x. So again, the whole idea is because the region bound doesn't start on the x-axis, if you rotate it, you're actually going to get a hole where this first function starts, and then the material would go to where the second function is. So we end up getting basically just a disk that has a hole in it, and we call it a washer. Now, this is going to make it a bit more complicated to get an equation for what the area is. So let's go to the next part and actually do it. So again, we'll just quickly label. So this is x is equal to a. And then this is going to be x is equal to b. Now, I'm just going to pick a point here. Okay, and again, it can be any point between A and B. I'll just pick it at 0.5 though. Okay, I'm going to draw a line here. Okay, and now what we need to do is we need to figure out what the area of that washer is. So the general idea with this is, so I'm just going to draw, again, quick little just three-dimensional picture of like what the washer. Okay, so here's my x-axis. Okay, so we've got my x-axis right here. Well, we don't need a vertical line there, so let's get rid of that, although unfortunately got rid of the rest of the shape too. Now, the way we want to calculate what the area of the washer is we would first of all just pretend like the washer is a solid disk, and then you just subtract the area of the hole. So what I would say is the area of the washer would be equal to the area of the entire circle, and then minus the area of the hole. Now, the area of the circle, again, let's just shade this in just to make the washer look a little bit clear. Okay, the area of the circle, we're going to give a name for what the radius of that is. So if I just draw this dimension to show what the area of the circle is, we're going to label that as being, I'm going to call it RO. Okay, RO would just be the outer radius. And then we're going to, the area of the hole here, we're going to call that RI. So RI would be equal to the inner radius. So now we can expand this a bit further. So what is the area of that washer? The area of that washer would be equal to, okay, area of the circle would be pi times RO squared minus pi times RI squared. Now, the thing is, though, when you make your way from the left towards the right, let's go back to my three-dimensional picture right here, the radius of the hole and the radius of the circle are going to be continuously changing. So we have to write down both radius values as a function. So we'll say, what is the area right here? So we'd have area as a function of x would be equal to, we would have pi multiplied by RO of x all squared minus pi times the inner radius as a function of x all squared. Okay, now we need to go to this picture and actually figure out what an expression is for the inner radius and figure out what an expression for the outer radius is. Okay, the inner radius is not hard to do. So if you look at the actual thing right here, the graph right here, okay, so this is what Ri of x would be equal to. Well, Ri of x would just be equal to the value of the green function at x. Now, remember, the green function, that is just the equation. Okay, so the green one right here, that was just y is equal to x squared. So that's just equal to x squared here. Now, the outer radius, so let's label that. So this is Ri. And then we're going to have the outer one here. So we'll call that RO of x. That would just be equal to the other function, okay? So, but we have to write it in as a function of x, though. So the other function is, here, we'll label it right here. So, because again, that's the height of the outer radius. It goes to the other function, but that one was written as x is, I don't want to call it a function because it fails a vertical line test, but the relation is x is equal to y squared. But again, we want to write down r as a function of x, so we'll just take the square root of both sides, and then we can do that. So then we would have square root, and then we would have, this would be equal to, we would have y would be equal to plus or minus the square root of x. So an expression for the outer radius right here is it would be equal to plus or minus the square root of x. So now I have an expression for the outer radius and the inner radius in terms of x. We're just going to sub it into this equation and then get an equation for the area of the washer as a function of x. Now, just one thing to note right here, there is a common pi, so we can factor that out. So this would then be a of x would be equal to pi, and then of, okay, RO of x, that's the expression for the outer radius. So that is, let's write that down here. So that's plus or minus the square root of x, and we're going to square that. And then minus pi times an expression for the inner radius, and the inner radius has is just equal to x squared. We're going to square that. And then let's simplify. So then we would have this would be equal to, oh, I guess I didn't actually factor the pi out. Okay, let's actually do that now. Okay, so factor the pi out, and then you would have, okay, the plus or minus is gone. So this would just turn into x here. And then minus x squared would become x to the power of 4. So we'd have a of x is equal to pi x minus x to the power of 4. Now, I'm not going to factor out the common x here because we're going to have to find the antiderivative of this expression in a moment. And if you do pull it out, it actually makes finding the antiderivative more complicated. So this is really the tough part. It's just mainly just getting an expression for what the area is as a function of x. And then now we just use the volume integration formula. So what we know is if I want to calculate the volume is equal to the integral in going from a to b of a of x dx. So in this situation, what we're doing is we're taking this three-dimensional shape, okay? We are breaking it into an infinite number of washers because we have, when you do the revolution about the x-axis, we have a hole now, okay? You take the thickness of one of those washers, you multiply by its cross-sectional area, and the integral from a to b tells me I'm putting all of those infinitely thin washers together. So let's write it down. Okay, a, we already did this calculation. We're going from 0 to 1. And then a of x was pi. And then x minus x to the power of 4. And we're going to integrate that with respect to x. So not a hard antiderivative to do, but let's pull that constant multiple out first. So the pi, bring it out here. And then evaluate. And then this would be equal to, okay, we'd have pi. And then we just have to find the antiderivative of x, which is x squared over 2. And then subtract, find the antiderivative of x to the 4, which is x to the power of 5 over 5. And then we're going to evaluate this from 0 to 1. There isn't really a constant multiple you can pull out of both these right here. So we'll just plug the numbers in and just calculate it. So this would be pi. Okay, so first time through, we're going to sub in 1. So we're going to have 1 squared over 2 minus 1 to the power of 5 over 5. And then minus, this would be 0 squared over 2. And then minus 0 to the power of 5, all divided by 5. So the nice thing is all of this stuff just goes away. So let's get rid of it. And then let's try to get a simplified expression now. So this would then be equal to, we'd have pi multiplied by, so we would have 1 over 2 minus 1 over 5. We need a common denominator here, so the common denominator between 2 and 5 is going to be 10. So we're going to multiply this by 5 over 5. We're going to multiply this by 2 over 2. And then we would get pi multiplied by, we would have 5 minus 2 over 10. And then I would get the volume would be equal to 3 times pi over 10. So the tough thing with these problems, especially with the washer method, is like you have to try to visualize like what is the three-dimensional shape you're actually forming, okay, which is kind of tough to do. And then it's usually a little bit tricky to get the area function, especially if it's a washer you're talking about. But usually the actual volume formula where you integrate, like once you have a of x, it's usually not particularly difficult to do, unless of course the functions that you're given in the problem are a bit annoying in terms of figuring out their antiderivatives. All right, one more. We already did part C there. So this is just a portion of a question from the AP exam. We actually did the part of the question A, which is find the area between those two curves in the previous lesson on area between two curves. You don't have to worry about this part right here. Okay, and then what we want to do is this time we're going to rotate it about a different line. Okay, so in the previous two examples, I did rotation about the x-axis, but you don't have to always rotate about the x-axis. You could rotate about something else. So it says here, write, but do not evaluate an integral expression that gives the volume of the solid generated when we take this region and we rotate it about the line y is equal to 4. Okay, so let's show what y is equal to 4 is because we're going to do a different rotation now. So let's draw this horizontal line. Y is equal to 4. Now, what I'm going to do is I'm going to show one of the disks. Okay, so let's pick, again, just some kind of an arbitrary point. So I'll pick a point that's going to be located, I don't know, it doesn't matter, just somewhere in between, because we're going to integrate it from, I guess we'd show the limits of integration as well. So let's clarify. So this is, this would be A. So we have A is equal to 0. And then we'll do this one, 2, that's B. Okay, B is equal to 2. Okay, let's do it about right here. Let's see what like the washer would look like. So again, notice if I do it right here, okay, the function itself doesn't go all the way down to the x-axis. So what that's going to be is that's going to be where your hole is. Now, we have to be a bit more careful with this because we're not rotating it about the x-axis. Actually, I'm wrong there. That's not going to be that would be the hole if we were rotating about the x-axis, but we're rotating about the y-axis. So let's draw a line that just goes from, again, my arbitrary point between 0 and 2. And let's draw a line that just goes up like that. Now, because I'm rotating it about the line y is equal to 4, this is now going to look a little bit different. So if you take this top portion here and you do a full rotation about a different axis of rotation, okay, this is now where the placement of the hole is going to be. And if you take this portion right here, because again, we're rotating this entire region there, so that this region is where you're going to actually form the solid, and you rotate that about the line, y is equal to 4, it's going to look like this. So we're rotating it relative to a different axis of rotation. Again, we'll just quickly like draw like a little element just to indicate the thickness right here. So again, your thickness, this would be dx, and then your cross-sectional area, that is going to be ax. Okay, so a of x. Now, what the question wants is it wants us just to set up an integral to calculate the volume of the solid, but we're not actually going to evaluate what that solid is. Now, we've already identified what an equation for the area of a washer is. So I do have a washer. So again, really that's just going to be the work is to figure out what that area equation is. So we're going to have the area. A as a function of x would be equal to, it's going to be pi. And then we're going to have the outer radius. So we'll say r o of x all squared, and then minus the inner radius ri of x all squared, close that off. Okay, I just factored the pi out right here, but basically it's just going to be the area of the circle subtract the area of the hole. Okay, So this is going to be a little bit more complicated to actually figure out just because we're not rotating it relative to the x-axis. So let's try to figure out what these different things are. So if I do, let's just do it as a different color here, just so this stands out a little bit. So the inner radius would be this dimension right here, okay? So this would be Ri of x. Now, to figure out Ri of x, what we're going to do is, okay, I'll show a couple things right here. So this full vertical distance, well, that's 4. Now, this distance right here, okay, we're kind of like going over to like where the side of the hole is right there, okay? Okay, so this distance, that would actually be the value of this function that's starting off and dipping down, okay? That's actually the cosine function. So what this one right here is this is actually going to be g of x. Okay, so again, this is the position of like where the hole is. This is Ri of x. So if I want to know what this inner radius is, what I would do is I would take this full vertical distance here, which is the distance from the x-axis of the line y equals 4, and then I would subtract g of x, because g of x is the value of the function, the y value of the function g of x. So my expression here would be 4 minus g of x. Now, as for the outer radius, well, that one's a lot easier to do. So your outer radius would be, maybe it's not super easy to do, but it's also not that too tough. So the outer radius, if I draw it, would be this right here. Okay, so this is going to be RO of x. Now, again, we'll do the same thing. We know the full vertical distance up here. So if I want to know what RO of x is, I just take 4 and have to subtract this little tiny piece right here. Again, just it's matching up with where the actual piece starts there. So this is actually the y value of this function that dips down and then goes up. That's the quadratic function. So this little distance right here would be f of x. So then R of x, RO of x would be equal to, you take this full vertical distance and you subtract this little chunk right here, which is f of x, and then that would be 4 minus f of x. All right, so let's write our area equation out now. So this would then be your area, A of x, would be equal to pi. And then we would have RO of x is 4 minus f of x, all squared, minus Ri of x, which is 4 minus g of x. So again, just notice this gets a bit tougher now when we choose a different axis to rotate about. So I have no idea why suddenly the word win is attached to like my cursor, but okay. All right, so okay, close that off there. I wonder if I just hit, okay, it's gone. No, I thought it was gone. Hold on a second. Okay, let's go back here. Sorry, I just, that was driving, it was annoying me. So let's see if it's gone now. No, it's still there. Oh, well, whatever. Okay, so now we have our area function. So now to get the volume, and again, it just says set up the integral, but you don't need to evaluate it. So again, volume is equal to the integral and going from a to b of a of x dx. So this would be equal to the integral and going from 0 to 2. And then 0 to 2 of pi bracket 4 minus f of x all squared minus 4 minus g of x all squared. Close that off, integrate with respect to x, and then I think that would probably be good enough in terms of leaving an answer because they already define f of x and g of x there. But if you want, you can actually sub the functions in. But this is as far as we're going to go. So we'll say v is equal to, we can pull the pi out. So we'd have pi integral from 0 to 2 of, in brackets, okay, 4 minus f of x. F of x is the quadratic function. 2x squared minus 6x plus 4. Square that. Okay, then subtract 4 minus the trig function, which would be 4 cosine of 1 over 4 pi times x all squared. Close that off. And if we actually did do this antiderivative, we would get the volume, but thankfully they were merciful on this exam and only required you to write down what the integral you're going to evaluate is, but they didn't require you to actually evaluate the integral. All right, so that's it for this lesson on volumes of solids of revolution. You can complete all problems in that section of the integration applications unit assignment. And then tomorrow we'll talk about how we can calculate volumes of cross sections. And I'll talk to you then.